Hello, we are the Mini Drone group, and throughout this presentation, we're going to talk about our progress throughout this semester. We have two technical directors, Dr. Sagano and Dr. Juan. My name is Nicholas DeLuiso. I'm a senior electrical engineer.
My name is Jacob St. Germain, and I'm a senior in electrical engineering.
My name is Heather Rojas, and I'm a senior computer engineer.
In the ICRL, it's an interdepartmental research group. They focus on the aerial robotics, industrial automation, soft robotics, human-robot interaction, multi-robot systems, and robotic swarms. Go next slide.
So our project motivation is that robotic swarms have the potential of widespread application. There's a lot of things that we can do with this. And the ICR Robots Lab already has a ground robotic swarm, and they would like to expand this. Now, the lab is too small for the drones that they currently have, and so smaller drones are needed in order to complete their research. Next slide, please. So the anticipated best outcome for our group is that we have a fully functional prototype of a single MAV that can be replicated to create a swarm. Now, this has certain constraints that we need to make sure that we don't go over. For example, the 0.6 kilogram weight. It has to be able to fit inside a 30 centimeter by 30 centimeter box. The flight time needs to be 10 minutes or more. It must be compatible with ROS, the robot operating system, through an onboard computer. It can orient using lab equipment, and it has to have a downward-facing camera.
A summary of our key team accomplishments this semester. We did select and order all our critical hardware and electronic components. We assembled all our drone components. We ensured our drone can communicate with our ground station computer. We completed flight simulations. We completed a flight test in the lab, and we set up our onboard companion computer and troubleshooted all issues that arose. The economic impact of this project, it should create additional graduate and undergraduate research opportunities within the lab, increase the scope of research that can be completed, and increase funding and grant opportunities for the program. I'm going to begin my portion of this presentation with a brief high-level project architecture, and we'll be talking about these components in more details coming right up. Software research, our team had to learn ROS. We also had to learn the PX4 firmware, which is what our flight controller uses. We use Q ground control software to interface with our firmware. We also learned Gazebo, utilized Ubuntu 18.04 as our operating system. All the tasks above were about a medium difficulty. Software integration was the more difficult part of the project. We had to ensure that all our software integrates correctly / ports to each other. We had to research and implement the ROS Mavlink communication located here. We had to implement changes to our firmware for our specific drone function, ideally off-board mode, and create documentation for the project. Our simulation environment was a low difficulty. We created a simulation where we could test software changes safely. Our simulation environment utilized Q ground control, our firmware, and Gazebo. We're also going to be implementing ROS. It will be integral for us to get our camera working and to practice more intricate off-board modes. Hardware integration was a high difficulty. We have an Android C4 connected to our flight controller via an FTDI adapter. Our SBC runs an ARM-based version of Ubuntu 18.04. This will be the brain of our drone, and the operating system is run on an eMMC, which is very fast compared to a microSD. Our future tasks will be to implement GPS, create camera drivers, test flight using the off-board control known as UAV. We'll also create a basic computer vision program and create the architecture to communicate with drone prototype number 2. Next up, we do have Jacob St. Germain.
So here's our high-level project architecture again. You can see it's very, very in-depth. You go next page. So choosing the hardware was one of our first tasks that we needed to overcome in order to have our fully functioning project. It was extremely important that we chose the correct parts for our capstone, since it was necessary for us to have a bunch of different requirements met. Our ESCs, which are the electronic speed controllers, our frame, our battery motors, our SBC, which is our single board computer, our flight controller, our power management board, and our camera were just some of the things that we needed to ensure that we had for the project. There are many requirements for our choices. For example, we needed to account for a lot of different things, such as the weight, the power draw from the computer, from the flight controller, from everything else, the camera, and we needed to ensure that it had the least power draw possible when compared to other things that we could have chosen. and compatibility too, which is very important. For example, our SBC, our single board computer, needed to run Linux and Ubuntu. Next slide, please. So the motor propellers and ESCs were very, very crucial to this project. We needed to ensure that we had the right ones for us to have a good flight and a good flight time. The propeller diameter was chosen after the frame size was picked. The motor stator size was chosen based after the prop size was chosen. After that, we had to choose a motor that would give us enough thrust to fly, but not too fast, because the faster it is, the more power usually that it was going to take. And so knowing that we needed to have that 10-minute flight time, we couldn't just take the strongest motor that we had. We had to compare each and every one and see which one would be a best fit for this project. After that, the ESCs were chosen through finding the max current draw of the motors. The ESCs basically act as a current limiter, so we don't have too much current flowing through the motors and ruining them. And so after we found that max current draw possible for the motor, we then chose the ESCs to be a little below that, just to ensure that we have working motors that don't end up breaking on us. Next slide, please. So the Odroid C4 was our SBC that we ended up choosing. It had it was able to host a Linux OS operating system, which is extremely helpful. We couldn't have done it without it. It was lightweight, even with the heat sink on it. It wasn't too heavy, and at the end of the day, it had the lowest power draw when compared to the other SBCs we looked into. Now, this is kind of larger compared to some of the SBCs we could have chosen, but it still nevertheless seemed to be the best fit project, best fit computer for our project. Next slide. So further research, we plan on building a second drone. We just got all the pieces in. I just need to go in and grab the pieces from the lab. We still have to implement the camera to the system. That's something that we do plan on doing soon. We have to complete the software integration. We have a good foothold in it right now, but there's still a lot of stuff we need to get into it to have a fully working prototype. And we need to either connect the drone to either GPS or the OptiTrack system in the lab, depending on whether or not we're able to go into the robotics lab next semester due to COVID. And next up is Nicholas DeLuiso for the rest of the project.
Thank you. For my portion of the slides, I'm going to be talking about the battery, the power management board, connector, the PixHawk Mini, and the FTDI. Go next, please. For the battery, we chose this LiPo battery with 1800 milliamps per hour. We chose this because Dr. Sagagno recommended a 1200 to 2000 milliamp per hour. And we chose the 1800 because it will make it more realistic for us to reach the desired 10 minutes for the flight time. Its weight is 68 grams. It's a 3-cell battery that has a EC3 connector and a 30C discharge rate. Go next, please. The power management board came with our PixHawk Mini, so we didn't have to select it. It has a XT60 wire connector, which came to be a little bit of a problem. It distributes power to ESCs, motors, SBC, and flight controller. As I mentioned, but actually, you can go next slide, please. As I mentioned, the battery has an EC3 connector, and the power distribution board has a XT60 connector, so we had to order this battery adapter. So one side will connect to the battery, one will connect to the PMB. For it to connect to the PMB, we had to cut the connection on one of the ends and solder on an XT60 connector, and then it fit right onto the battery. And then the last one will connect to the Odroid C4. We haven't gotten to that yet, but that's right around the corner. You can go next, please. This is the flight controller we chose. Is the PixHawk 4 Mini. It's extremely lightweight and very small. It's the brains of our operation. The PX4 is the firmware and the open source that goes along with this, and it's very user friendly. It came with a GPS module, which ended up being extremely useful because we're going to have to implement that in our next steps. You can go next, please. The FTDI adapter, it's a USB to serial adapter. You have the pinouts right there, the receiver, transmitter ground voltage. It supports 3.3 and 5 volts, and it connects to the Pixoc Mini serial port, and the other end connects to the ground control computer. You can go next, please.
So here we have a video of our prototype in action. So right now you're going to see me moving my hands to the left and to the right, and then you're going to see the drone react with that. And that's what the flight controller's main mission is to do, is to ensure that the drone's flying straight up, or rather balanced. So you see there that when I move my hand either to the left or to the right, it starts to move some of the propellers in a different way so that it can stay straight up.
A summary of our future accomplishments that we plan to have in the spring. We'll implement the GPS. We'll flight test using off-board mode using ROS. We'll integrate our camera. We'll ensure our flight time is met. We'll cut down excess weight to meet our weight requirement. We'll construct prototype number 2. We'll demonstrate the swarm algorithm, and we'll integrate in the lab with OptiTrack.
For our key acknowledgements, we would like to thank our 2 technical directors who sponsored this project and gave us the opportunity to gain this experience, and Dr. Sunak for putting all of this together and making this possible. Thank you.
Thank you, everyone.
Thank you.